decades of searching, every piece of evidence we gathered from Mars always pointed to the same number: 0. That was until Perseverance sent back a series of photos of a rock, featuring strange, leopard-like spots that scientists call biosignatures, the signs of life. This isn't the first time we've held on to hope. In 1996, NASA announced they had found fossilized bacteria in a Martian meteorite.
The readings indicate a deviation.
The whole world held its breath. Then it all collapsed. But this time is different. It's not because scientists are more certain. It's because for the first time they cannot provide any other explanation more convincing than the answer we are all hesitant to say out loud. If this isn't a trace of life, then what is it? Welcome to Astrexo. Today, we will explore what Perseverance has just discovered on Mars. In February 2021, a massive machine touched down on the surface of Mars. Not at a random location, but right at the heart of a place that once held water. Perseverance rover landed inside Jezero Crater, an ancient lakebed that dried up billions of years ago, where rivers once flowed in and out, forming deltas and leaving behind layers of sediment like a vast geological record. Jezero Crater is not just a crater on Mars. It is evidence that this planet was once wet, once had water, and may have once had the conditions necessary for life to exist. The soil here is rich in clay minerals, a type of material that only forms when water is present over long periods of time, and that is exactly why the Perseverance rover was sent here. Not to find life that still exists, but to trace the remnants of life that disappeared long ago, possibly preserved as ancient microbes frozen within rock. If there is any place on Mars that was once suitable for life, this is almost certainly one of the strongest candidates. But it does not stop there. Ancient lakebeds like Jezero Crater may also contain compounds such as perchlorid, a substance that, on Earth, some microorganisms can use to survive in extreme environments. That is why astrobiologists are not only looking at Mars, they are also studying organisms that live in extreme conditions on Earth to understand just how far life can adapt. And the mission of the Perseverance rover is incredibly clear: to search for the faintest possible signs of life, to identify the most valuable rock samples, and to store them for a future mission that will bring them back to Earth, where for the first time in history, we may be able to directly test whether life has ever existed beyond this planet. One day in July 2024, while moving along the edge of an ancient river channel known as Neretva Vallis, the Perseverance rover detected something unusual. This region was once shaped by flowing water across the surface of Mars in the distant past. And right there, a rock formation known as Bright Angel drew attention. But what mattered was not its outer appearance, it was what lay within. Two advanced instruments, Pixel instrument and Sherlock instrument, began scanning the surface and revealed that this was a sedimentary rock formed from clay and silt. Materials on Earth well known for their ability to preserve traces of microorganisms over extremely long periods of time. That discovery prompted the Perseverance rover to take a closer look. And what it found truly caught the attention of the scientific community. This rock, later named Chayava Falls, contains organic compounds such as carbon, phosphorus, and iron. But not in a random distribution, instead arranged into clearly defined circular structures. These tiny features, known as leopard spots and poppy seeds, range in size from about 200 micrometers to 1 millimeter, incredibly small. Yet it is their organized structure that matters most. In biology, patterns like these rarely appear by chance, and that detail alone is enough to push astrobiologists to ask a serious question. Could these be the lingering traces of life that once existed on Mars? The bright cores inside these leopard spots are nearly indistinguishable from the surrounding rock. But the dark rims encircling them tell an entirely different story, where iron and phosphorus are concentrated at unusually high levels, forming a sharp boundary as if a localized chemical transformation had once taken place. These signatures point toward iron reduction, a reaction that on Earth is often directly linked to microbial activity in water-rich environments. The Perseverance rover did not stop there. It also detected carbon-based organic compounds scattered throughout the rock's structure. And when all the data is brought together, from morphology and geochemical composition to mineral traces, scientists began to arrive at a critical conclusion. This rock almost certainly interacted with water in the past. On Earth, when organic matter, water, and iron reduction occur together within a system like this, the most familiar explanation is almost always the presence of microorganisms. And in that moment, everything shifted, because NASA was no longer just observing a rock. They were holding something that could be truly one of a kind. Could this ancient mass of mud really preserve the first biological signature beyond Earth ever discovered by humanity? The key to this discovery lies in two specific minerals: vivianite and greigite. Vivianite is an iron phosphate mineral, and on Earth it typically forms in sediment-rich, water-rich environments where certain microorganisms can quite literally consume iron in a chemical sense. Instead of using oxygen like we do, bacteria such as Geobacter generate energy by transforming iron in their surroundings, absorbing oxidized iron and releasing it in a reduced form. When that reduced iron interacts with phosphate and water, vivianite can form. Greigite adds another layer to the story, because on Earth it is often associated with microorganisms capable of sulfate reduction, producing sulfide, which then combines with iron. In other words, both of these minerals can emerge in environments where microbial life actively participates in the chemistry of its surroundings. But science cannot afford to jump to the most compelling explanation too quickly. So, if not microbes, what else could drive these reduction processes? One possibility is extremely high temperatures. The sulfide required for greigite could originate from volcanic gases seeping into groundwater. But this hypothesis immediately runs into a major problem. It requires a nearby heat source or hydrothermal system powerful enough to introduce these compounds into the rock-forming environment. And so far, the region around Cheyava Falls shows no clear evidence of such volcanic or hydrothermal activity. Another hypothesis, at first glance more plausible, is that sulfate within the rock was directly reduced into sulfide through reactions with organic compounds already present in the environment. But as soon as the details are examined more closely, the problem reappears. On Earth, reactions of this kind only occur to a meaningful extent when temperatures exceed roughly 150 to 200 degrees Celsius, and even under those conditions, they require a significant amount of energy and proceed extremely slowly. That makes this scenario unlikely, especially since geological analyses of the surrounding region show no evidence of high temperatures in the past. In other words, there is no indication that the environment here was ever hot enough to drive sulfate reduction and produce Griegite in this way. As the thermal hypothesis begins to fall apart, another explanation starts to emerge, one that centers on acidity. Under acidic conditions, both iron and sulfate ions become far more soluble in water, increasing the likelihood of reduction reactions occurring purely through chemistry, without any involvement from life. If ancient Martian water was more acidic than we once believed, then that environment alone could have produced the structures now observed by the Perseverance rover. And if that is the case, then these strange spots may not be traces of life at all, but simply the result of chemical processes unfolding on an alien world. But then a small detail emerged, and it changed the way we look at the entire problem. Right near the sampling site, the Perseverance rover detected an extremely tiny green mineral grain, a remnant of olivine preserved within the rock. It may sound insignificant, but its presence delivers a direct blow to the acidic environment hypothesis. Olivine is one of the most easily destroyed silicate minerals when exposed to water, especially under acidic conditions. Unlike more stable structures such as silicon dioxide, it is not locked by strong silicon-oxygen-silicon bonds, but exists as negatively charged silicate ions loosely bound to positively charged magnesium and iron ions. When the environment becomes acidic, hydrogen ions rapidly replace those bonds, causing the structure to collapse, breaking down into orthosilicic acid and releasing magnesium into solution. In other words, if the water here had truly been highly acidic, olivine would have had almost no chance of surviving. Yet it is still there, nearly intact. And that fact alone is enough to eliminate one of the most plausible chemical explanations. As the acidic environment hypothesis begins to fall apart, the original question returns, but this time with far greater weight. If it was not temperature, not acidity, then what created those strange structures? Science, at its deepest level, is not a journey to prove something right, but a continuous process of trying to prove it wrong. Every hypothesis must endure the pressure of skepticism, tested, challenged, and stripped of possibilities one by one. And over time, as more explanations are eliminated, what remains begins to stand out, not because it was confirmed from the start, but because it is the only thing that has not collapsed under the weight of evidence. If an explanation can survive long enough against doubt, withstand enough tests, it gradually rises into a testable theory, strong enough to be accepted by the scientific community. Following that logic, the Mars research team approached the problem in a way that runs counter to intuition.
Choose wisely.
They did not try to prove that what the Perseverance rover found was evidence of life. Instead, they began with the null hypothesis that everything observed was purely the result of chemical processes. From there, they systematically tested every non-biological scenario, from high temperatures and acidic environments to other geochemical reactions. But after months of analysis, comparison, and elimination, they arrived at a striking conclusion. They could not find a single abiotic explanation capable of fully accounting for what had been observed. But there is a very clear boundary that science is not allowed to cross. Saying, "We cannot explain this phenomenon through abiotic processes," is fundamentally different from claiming this is evidence of life. All the excitement, all the hypotheses being built right now are ultimately grounded in our understanding of biochemistry on Earth. And that is precisely the problem. Because nothing guarantees that the familiar rules here will repeat themselves in the same way on Mars. What we are seeing may have nothing to do with life as we know it, but instead could be the expression of an entirely alien chemical system, something we may not even yet have the framework to describe.
The readings are stable, but we're seeing
That is why NASA must remain extremely cautious, avoiding premature conclusions, because history has already shown how easily we can be misled. In 1976, the Viking program carried out what seemed like a very direct experiment, supplying nutrients labeled with radioactive carbon into Martian soil and waiting to see if anything would consume them. The results shocked the world, because the signal looked exactly like the metabolic response of microorganisms. In that moment, many believed we had found extraterrestrial life. But decades later, the Phoenix lander uncovered a detail that changed the entire story. Martian soil contains high levels of perchlorate, a powerful oxidizer capable of breaking down organic compounds and releasing gas when heated. What was once seen as a biological signature turned out to be a sophisticated chemical reaction. A misleading result, but one that serves as a reminder. In the search for life beyond Earth, the most dangerous mistake is not failing to see what is there, but rushing to believe what we want to see. But despite all the missteps of the past, Mars has always had a way of pulling us back into hope. In 1996, a meteorite known as ALH 84001 shook the scientific world. This rock is more than 4 billion years old, formed during a time when Mars still had liquid water on its surface, and when examined under an electron microscope, it revealed tiny structures resembling clusters of bacteria. In that moment, everything seemed to pause. The idea that we might be looking at fossils of extraterrestrial life was simply too powerful to ignore. The excitement spread so widely that Bill Clinton made an official statement about the discovery. turning it into one of the most talked about scientific announcements of its time. It sounds familiar, doesn't it? Almost identical to how the world is reacting to what the Perseverance rover has just uncovered. But as time passed, and as it has so many times before, reality began to surface. By 2022, those structures once believed to be traces of microorganisms were reinterpreted as the result of a process entirely unrelated to life. A reaction between water and rock known as serpentinization. Those lifelike shapes turned out to be nothing more than products of inorganic chemistry. And once again, hope was pulled back down to Earth. So, in the end, what we have just seen in Jezero Crater, is it a genuine breakthrough, or just another moment of almost touching the truth, like so many times before? Is this yet another illusion shaped by chemistry, or the point where everything finally begins to change? That question has only one way to be answered, and this time, we cannot rely solely on remote data. We have to bring those samples back to Earth. That is where the Mars Sample Return mission enters the stage, one of the most ambitious and complex plans humanity has ever designed. The entire operation requires coordination between multiple spacecraft, each performing with near-perfect precision in a tightly sequenced chain of events. The first phase has already been completed by the Perseverance rover, which drilled directly into the Chayava Falls rock and sealed an extremely valuable core sample known as Sapphire Canyon. Next, another lander will be sent to the Martian surface, touching down near the rover's location, collecting the sample tubes it has left behind, and then attempting something never done before: launching them off the surface of Mars into orbit. In the final step, an orbiter will rendezvous with those samples in space, retrieve them, and carry them back to Earth. Only when these rocks are placed inside our laboratories, under instruments no robot on Mars could ever replicate, will we truly know whether we are standing before a historic discovery, or facing yet another reminder that the universe is far more complex than we ever imagined. This is not just an ambitious mission. It is a scientific gamble worth about $11 billion. Mars Sample Return was announced in 2022 as a joint effort between NASA and the European Space Agency, with the goal of bringing back the first rock samples from Mars. But since then, reality has begun to set in. Costs have surged, technical challenges have proven more complex than expected, and uncertainty around funding has repeatedly pushed the timeline back, from a target of 2033 to as late as 2040, before ultimately slipping into an indefinite delay. This has happened even as the National Academies of Sciences, in its decadal survey reports, ranked the Mars Sample Return as the top scientific priority for NASA in 2 consecutive cycles. What is even more striking is that all of those decisions were made before the potential biosignatures at Jezero were discovered. Now, as the question of life beyond Earth becomes more tangible than ever, this is no longer just about science. It has become a matter of will and priority. At this point, all we can do is wait and see whether pressure from the scientific community and growing public attention will be enough to push leaders back toward committing to this mission once again. So if one day we truly succeed in bringing the Sapphire Canyon sample back to Earth, what will scientists actually do with it? The answer is that they will not simply look at it, they will dissect it at a level no instrument on Mars could ever achieve, searching for the most delicate chemical fingerprints of life. One of the first critical signs is chirality. Amino acids, the building blocks of life as we know it, exist in two mirror image forms, a left-handed and a right-handed version known as L and D. Yet on Earth, something remarkable happens. Life almost exclusively selects one side. Living organisms use L-amino acids nearly entirely, while non-living matter shows no such preference and typically appears in a balanced ratio. If a clear imbalance appears in samples from Mars, whether left or right, it would no longer be a minor detail, but a powerful signal that some form of biological selection may have taken place. The second fingerprint lies in carbon isotopes. Carbon does not exist in just one form, but commonly appears as two stable versions: carbon-12 and carbon-13. On Earth, living organisms tend to prefer carbon-12, creating a distinct ratio compared to non-living material. If samples from Sapphire Canyon reveal a similar pattern, showing a measurable bias toward carbon-12, it would serve as a second independent clue pointing in the same direction. No single piece of evidence is enough to draw a conclusion, but when multiple fingerprints begin to align, we move dangerously close to an answer humanity has been waiting for a very long time. You see, the way we usually look at discoveries like this is fairly simple. Either it is a sign of life or it is not. But for NASA, nothing is ever allowed to be that simple. They approach the problem through levels of confidence rather than absolute conclusions. Recently, NASA proposed a framework known as the Confidence of Life Detection Scale, a system built on multiple criteria designed to assess how certain a potential discovery of extraterrestrial biology truly is. This scale consists of 7 levels, starting from the lowest, where we only have signals that could be related to life, all the way to the highest, where multiple independent research teams across repeated testing converge on the same conclusion. What matters is that there are no leaps here. Each level demands stronger evidence and more rigorous validation than the one before. As of now, NASA has not officially placed the findings at Jezero Crater at any specific point on this scale. But based on what we know, it likely sits somewhere in the middle, where the signals are becoming compelling, yet not strong enough to confirm. If, in the future, the samples are returned to Earth and multiple independent laboratories around the world verify a biological origin, we will move toward the higher levels, where doubt begins to narrow. And to reach the very top, where uncertainty is nearly gone, we may have to return to Mars once again, finding similar evidence in an entirely different location, as a final confirmation that what we are seeing is not coincidence, but a pattern. So, when NASA says this could be the clearest sign of life ever found on Mars, they are not claiming it is life. They are pointing out that we are approaching the boundary of an answer. Everything now depends on the Mars sample return, because only when these samples are brought back to Earth can we verify them with certainty. Whatever the outcome, its value will be immense, because Mars is like a time capsule. preserving ancient conditions that Earth has long since lost. Studying this planet is not just about searching for life, it is also about looking back at our own origins. But if those samples truly carry biological signatures, everything will change instantly. It would prove that life is not unique, and at the same time open up even bigger questions. Are life on Earth and Mars connected, or did they emerge independently? And if it happened here, how many other places across the universe could it happen as well? In astrobiology, there's an idea known as none-one infinite. Life either does not exist anywhere, exists in only one place, or emerges everywhere across the universe. We already know it is not none. If it is one, then we are truly alone. But if it is two, if both Earth and Mars have hosted life, then there is no reason to stop at that number. It could be thousands, millions, or even countless other places. And at that point, life would no longer be something rare, but something woven naturally into the fabric of the universe. And perhaps, paradoxically, that realization would make us look back at this planet and value each other even more. And here our journey comes to a pause, not with a clear answer, but with an even greater question. The kind that makes documentary about space so compelling. Are we truly alone, or have we only just begun to understand this universe? If you are someone who loves space, thank you for staying until the end of today's story. Share this video, leave a comment with your thoughts, and if you want to keep exploring mysteries like this, do not forget to subscribe and hit like so you do not miss what comes next, from Mars to the Moon and far beyond. Goodbye, and I will see you again on the next journey.